Hello dear students, Assalamu alaikum. My name is Engineer Mir Masood Shah. I am lecturer Department of Technology, Sarhad University of Science and Information Technology, Peshawar. The subject I am teaching you is fluid mechanics and this subject is for BTech Civil and the credit hour for this course is 2 and today is your lecture number 2. In lecture number 2, the first topic we will study about pressure. So what is pressure? We see that whenever a liquid such as water, oil, etc. is contained in a vessel, it exerts force at all points on the sides and bottom of the container. This force per unit area is called pressure. So the force per unit area is called pressure. If P is the force acting on area A, then intensity of pressure P is equal to P divided by A. Here P is the force which is applied per unit area. So pressure is equal to force per unit area. As we put or contain water or any other liquid in a vessel, normally it exerts pressure on the sides as well as on the bottom of the container. So this force which exerts on the sides and bottom of the container per unit area is called pressure. The unit of force is Newton and the unit of area is square meter. So the unit of pressure is Newton per square meter or Newton per square millimeter, which is also equal to Pascal. Next is pressure head. Consider a vessel containing some liquid as shown in figure. Here is the figure 2.1 in which a vessel contains some liquid. We know that the liquid will exert pressure on all sides as well as bottom of the vessel, as we already studied that whenever liquid is contained in a vessel, it exerts pressure on the side as well as on the bottom of the vessel. Now let a bottomless cylinder be made to stand in the liquid as shown in figure. Here is a bottomless cylinder which is put in this vessel. Let omega is equal to specific weight of liquid. This small w is known as omega and it is equal to specific weight of liquid. The liquid which is contained in this vessel having a specific weight of omega. H is equal to height of the cylinder. H is equal to height of the liquid in the cylinder. So H is the height of liquid in this cylinder and A is equal to area of the cylinder base, and A is the area of this cylinder base. A little consideration will show that there will be some pressure on the cylinder base due to the weight of the liquid in it. Already we have studied that whenever a liquid is contained in a vessel or a cylinder, it exerts pressure on the base of the cylinder. So in this case a cylinder is immersed in this liquid, so the liquid in this cylinder will exert a force on the base of the cylinder due to the weight of the liquid. Therefore pressure P is equal to weight of the liquid in the cylinder divided by area of the cylinder base. So the pressure is equal to the weight of the liquid in the cylinder. the liquid which is contained in this cylinder is equal to the force of liquid at the base of the cylinder, and A is the area of the cylinder base. Here the area A is equal to area of the cylinder base. So weight of the liquid in the cylinder is equal to omega H into A, means the total weight of the liquid in the cylinder is equal to volume into unit weight. Omega is the unit weight of the liquid in the cylinder, H is the height of the liquid, and A is the area of the cylinder. So when we multiply H by A, we will get the total volume of the cylinder, and when we multiply it by omega, we will get the total weight of the liquid in the cylinder, and divided by area of the cylinder base, which is equal to A. So A will cancel out with A, and pressure head will be equal to omega H. This equation shows the intensity of pressure at any point in a liquid is proportional to the depth from the surface. As omega is constant for the given liquid, it is thus obvious that pressure can be expressed in either of the following two ways. Number one, as a force per unit area, that is Newton per square meter or kilonewton per square meter, etc., which is equal to Pascal or kilopascal. And number two, as a height of the equivalent liquid column. The equation P is equal to omega H shows that pressure intensity is directly proportional to the liquid depth. As the liquid depth increases, the pressure intensity increases, and vice versa. For a given liquid, means that if the omega is constant, also the units are expressed in the following two ways: as Newton per square meter or kilonewton per square meter, which is equal to Pascal, and this one is equal to kilopascal. Newton per square meter is equal to 1 Pascal. Also, it is equal to the height of the equivalent liquid column. The intensity of pressure in brief is generally termed as pressure. So the intensity of pressure is also known as, or generally termed as, pressure. Note, the pressure is always expressed in Pascal, briefly written as PA, as already been explained, such that 1 PA is equal to 1 Newton per square meter, and 1 kPa, and 1 kilopascal, is equal to 1 kilonewton per square meter, and 1 megapascal is equal to 1 meganewton per square meter, or 1 Newton per square millimeter. We have example 2.1. Find the pressure at a point 4 meters below the free surface of water. In the statement, we have to find pressure at a point which is 4 meters below the free surface of water. So solution is, first of all, we will write given data. In given data, H, which is the depth, is given, is equal to 4 meters, and we have to find pressure P. So P is unknown, as we know that pressure at that point, or pressure at the point P, is equal to omega H. Omega is equal to 9.81, since the liquid is water and the unit weight or specific weight is equal of water is equal to 9.81, and depth H is equal to 4 meters already given. So P is equal to 9.81 multiplied by 4 is equal to 39.24 kilonewton per square meter, which is equal to 39.24 kilopascal. And this is the answer of our example 2.1. Example 2.2. A steel plate is immersed in an oil of specific weight 7.5 kilonewton per cubic meter up to a depth of 2.5 meter. What is the intensity of pressure on the plate due to the oil? In example 2.2, the specific weight of oil is given, which is 7.5 kilonewton per cubic meter, and a steel plate is immersed in this oil up to a depth of 2.5 meter. We have to find the intensity of pressure on the plate due to the oil. First of all, we will write the given data. In given data, specific weight, which is unit weight of oil, is given, which is equal to omega equal to 7.5 kilonewton per cubic meter, and also the depth is given, which is 2.5 meters, so H is equal to 2.5 meter. We know that intensity of pressure on the plate P is equal to omega H, so omega is given 7.5 and H is also given 2.5. So pressure intensity on the plate due to the oil is equal to 7.5 multiplied by 2.5 equal to 18.75 kilonewton per square meter, which is equal to 18.75 kilopascal. And this is the answer of our example 2.2. In example 3.3, the statement is calculate the height of a water column equivalent to a pressure of 0.15 megapascal. In the example 2.3, we have to find or calculate the height of water column, and the pressure is given, which is equal to 0.15 megapascal. So given data, in given data we have P is equal to 0.15 megapascal, and we have to find the value of H, which is the water column. Water column equivalent to a pressure of 0.15 megapascal. So we know that pressure of the water column P is equal to, the basic equation is P is equal to omega H. So in pressure, the pressure of value is given, which is equal to 0.15 into 10 raised to power 3, which is equal to omega H, and the value of omega is 9.81, which is the value of water, and H is to be find out. So divide 0.15 into 10 raised to power 3 by 9.81, and we will get the value of H, which is equal to 15.3 meter. And this is the answer of example 2.3. Next example is example 2.4. The statement is, what is the height of an oil column of specific gravity 0.9 equivalent to a gauge pressure of 20.3 kilopascal? We have to find the height of an oil column for specific gravity 0.9 and a gauge pressure of 20.3 kilopascal. First of all, we will write the given data. In given data, we have specific gravity of oil, which is 0.9, and gauge pressure of 20.3 kilopascal, which is equal to 20.3 kilonewton per square meter. Let H is equal to height of the oil column in meters. First of all, we know that specific weight of the oil omega is equal to 0.9 multiplied by 9.81. As specific gravity, we already studied in lecture number 1 that specific gravity is equal to specific weight of the liquid divided by specific weight of pure water at 4 degrees centigrade, which is 9.81. So to find the specific weight of oil, we multiply the specific gravity by 9.81. So omega is equal to 8.829 kilonewton per cubic meter, which is the specific weight of oil. And now to find the value of H, we have gauge pressure P is equal to omega H. P is already given, which is 20.3 kilonewton per cubic square meter, and omega we already find out it, which is 8.829, and the value of h is to be determined. So divide 20.3 by 8.829, we will get the value of h, which is equal to 2.3 meter. So this is the answer of example 2.3. Next topic we have is Pascal law. It states the intensity of pressure at any point in a fluid at rest is the same in all directions. That the pressure intensity on all the sides or at any point in a fluid which is at rest is the same in all direction, and this is the statement of Pascal law. To prove the Pascal law, we will consider a very small right angle triangular element ABC of a liquid as shown in figure 2.2. We consider a small right angle triangle element with ABC as shown in figure 2.2. Let Px is equal to intensity of horizontal pressure on the element of the liquid. Px is equal to intensity of horizontal pressure on the element of the liquid. Py is equal to intensity of vertical pressure on the element of the liquid. This is Py, which is the intensity of vertical pressure on the element of the liquid, and Pz is equal to intensity of pressure on the diagonal of the triangular element of the liquid, and this is Pz, which is diagonal intensity of pressure on the diagonal of the triangular element, and theta is equal to angle of the triangular element of the liquid. This is the theta. Now pressure on the vertical side AC of the liquid, Px is equal to small px into AC. So the pressure on the vertical side is equal to Px into this AC side. Similarly, pressure on the horizontal side BC of the liquid is equal to Py is equal to small py into BC. So this is the pressure on the horizontal side BC, which is equal to small py into BC. And the pressure on the diagonal AB of the liquid, this is the diagonal AB, and the pressure on it is equal to capital PZ is equal to small pz into AB, and this is the pressure on the diagonal AB. Since the element of the liquid is at rest, therefore sum of the horizontal and vertical components of the liquid pressure must be equal to 0, as we already considered that the element of the liquid is at rest. So the sum of the horizontal and vertical components of the liquid pressure must be equal to 0. Now resolving the forces horizontally, Pz sin theta is equal to Px, as sin theta is equal to perpendicular divided by base. So on perpendicular divided by hypotenuse, sin theta is equal to perpendicular divided by hypotenuse. So perpendicular is Px and hypotenuse is Pz. So sin theta is equal to Px divided by Pz, which so multiply Pz on both sides, we will get Px is equal to Pz sin theta, or small pz AB, which is the value of capital PZ. Already find out capital PZ is equal to small pz AB. Put this value in place of capital PZ. Sin theta is equal to small px AC. Small capital Px is equal to small px AC. From the geometry of the figure, we find that AB sin theta is equal to AC, means the geometry of from the geometry of the figure, sin theta is equal to perpendicular divided by hypotenuse. So perpendicular side in the geometry, perpendicular side is AC and the hypotenuse side is AB. So sin theta is equal to AC divided by AB, and then multiply AB on both sides. We will get AB sin theta equal to AC. Now PZ dot AC is equal to PX dot AC. As in this equation, PZ AB sin theta is equal to PX AC. So as AB sin theta is equal to AC, so put this AC value in this equation and we will get this equation to be PZ AC equal to PX AC. Now AC will cancel out with this AC and we will get PZ is equal to PX. Now resolving the forces vertically, that is PZ cos theta is equal to Py minus W, where W is equal to weight of the liquid element. As cos theta is equal to base divided by hypotenuse, so at the base the forces are Py and the weight of this liquid element which is against this Py, so Py minus W is the total force at the base of the triangular element, and on the hypotenuse the forces are Pz. So multiplying both sides by Pz, Pz will cancel out with Pz on the right side, and on the left side we will get Pz cos theta equal to Py minus W. Now since we are considering a very small right triangular element of the liquid, therefore neglecting the weight of the liquid, so we find out that Pz cos theta is equal to Py. As the triangular element we considered is so small and the weight of this triangular element is negligible, so we neglect the weight of the triangular element, and this equation comes out to be Pz cos theta is equal to Py, as W means weight of the liquid is neglected, liquid particle is neglected. So this equation comes out to be Pz AB cos theta equal to Py BC. Pz AB is the value of Pz, capital Pz, which is capital Pz is equal to small pz AB, and capital Py is equal to small py BC. So these are the values of capital Pz and capital Py. Now similarly, from the geometry of the figure we find out that cos theta is equal to base divided by hypotenuse. Base is BC while hypotenuse is AB. So cos theta is equal to BC divided by AB. Multiply both sides by AB. AB will cancel out with AB and we will get AB cos theta is equal to BC. Now in this equation put the value of AB cos theta, which is BC, and this equation comes out to be PZ BC equal to Py BC. BC will cancel out with BC and we will get PZ equal to Py, which is equation number 4. Equation number 5. Now from equation 4 and 5 we find out that Px equal to Py equal to Pz. Since Pz equal to Px and also Pz equal to Py, so this means Px equal to Py equal to Pz, and thus the intensity of pressure at any point in a fluid at rest is the same in all directions, which is the proof of the Pascal law. And this is the end of our today's lecture.